Here we want to find this derivative for this function, and which is at first it's a bit tricky, because this is the kind of function where they give it to you and they tell you the derivative of this is that. So that's not so good. There are multiple ways to do this, but the way I like to do it, which I will be carrying out in this video, is using implicit differentiation. So how does this work? Well, you take your function, you give it a name, say y. So if you ask me why, I tell you, yeah, it's because I want to. So it's a to the t. This is my function, and if I have problems with this and I don't know how to differentiate it, then I better get it in a format which I can differentiate it. And so in this case, I think it would be a good idea to introduce the logarithm. The reason for this is because I have my variable in the exponent, which I want to differentiate, and I don't know how to differentiate things which are not constants when they are in the exponent. So notice that this is very different from, for example, x to the a, or we could say t to the a to be consistent. So here the variable is t, there also the variable is t, but the constant is there. And if the exponent is constant, then I can take the derivative, and then it's at to the a minus 1. If this exponent is a constant. But when you have the opposite way around, it's a completely different thing. And so, because I'm more comfortable with my variables on the ground, I will indeed introduce my ln function. So ln of y will be ln of a to the t. But then this is nice because I can use one of the properties of the logarithmic function, which tells you that if you have ln of x to the something, you can just bring out this something as a coefficient. So this is precisely what I'm going to do now. I get t times ln of a. And now I have some ideas. Now I can take the derivative of this thing. I'm not sure what's happening there really, but I know what's happening in here. So let us, for example, take the derivative and see what we will get. So we take the derivative of both sides. With respect to t, very important. So this gives us the following. I want to leave the derivative of ln of y for now. I'll just write it as it is. As for the other side, this will simply be so we have t, we have ln of a. And I want you to observe something now. We're multiplying two things together. So we should apply the product rule. So one time it will be the derivative of t times ln of a plus the derivative of ln of a times t. But here's the catch. Ln of a is a constant. And so if you take the derivative of a constant, it's just 0. So this is 0, so actually the whole term is 0. And so I don't need to write this down. All I need to do is just worry about this expression. But even this expression is not too difficult because the derivative of t is 1. You could do this in multiple different ways, but the simplest one is you bring the 1 down, and then you have t to the 1 minus 1, which is 0, and anything to the power of 0 is 1. We have 1 times 1, which is 1. Now I'm kind of hand-waving this because it's obvious, to some extent. So this is good. We know now that the derivative of t times ln of a is ln of a, but we still need to take the derivative on the other side. And so the second fact of the day that we will be using is that the derivative of ln of x is 1 over x. So the derivative of ln of y would be 1 over y. Almost. And we'll see that in a moment. So indeed, we will get one over y. But then notice that y is not t. So we need to apply the chain rule. It could be the case that there is a certain rate of change of y with respect to t. So we need to factor that in. So that is important when you're differentiating with respect to different variables. You always need to take care of the chain rule in that case. So this is equal to that, which is already very good. We're very, very, very close to our solution. So far, this is what we've obtained. And I claim that we're very close to the solution because here's the catch. I make an asterisk here. If y is equal to a to the t, then the derivative of y with respect to t is the derivative with respect to t of a to the t. That should make perfect sense. But then the trick here is to notice that this is what we want to find, and this is equivalent to it, and we have it in an equation. So we can solve for this dy by dt to obtain our solution. So dy by dt, I will just multiply by y as long as y is not equal to 0. This y. Because y is a to the t. So I multiply by y, and I get that dy by dt is equal to ln of a times what? Times y. But why? Okay, that was a silly joke which did not fit the context. But you just multiply both sides by y. I've repeated this multiple times. Now again, notice that y is equal to a to the t. So I can replace y and I can write ln of a times a to the t. So dy by dt is equal to this. It's number 1. And number 2, dy by dt is equal to that. So from 1 and 2, we get that the derivative with respect to t of a to the t is just equal to ln of a times a to the t. We just need an equal sign here. This is because feel like I went back to the 17th century or something. Yeah, because both of them are equal to dy by dt. And so that is why, in that case, they would be equal. As I've already mentioned, there are multiple different ways of doing this, but I prefer this because it focuses on the skill of implicit differentiation. And it teaches you a skill, and that is when you have your variables as exponents, you should apply the logarithm, because it is very difficult to work and to move forward otherwise.